Hello class. We are in section 510 today for Algebra 1. We are looking at rate of change today. So it starts out here talking about linear equations. So linear equations are equations that make lines. So if we're thinking about what that form would be like, it's y equals mx plus b. And they have a blank rate of change. So because you have that slope, that constant slope, this is going to be a constant rate of change. So each point, remember we would count how many squares up and how many squares over, do rise over run, use the slope to get from one point to another, and that was always the same. That's what made them a straight line. So this is a constant rate of change, and then above it, I'm going to write the word slope. This means that the rate of change is the same for the entire graph. So exponential functions do not have a constant rate of change. Rather, it changes depending on which region of the graph you are evaluating. So let's think about what that equation looks like. Exponential functions are in the form y equals a times b to the x power. So remember what happens is that we are like multiplying b over and over and over again. B is our growth factor or a multiplier. So if we're multiplying, it's going to change a lot more rapidly if we look at multiplying by something bigger than 1. And so we can't just connect our points with a straight line. They're going to end up being a curve. So that's how our notes start out. Let A be the function that models the area A of t in square yards of algae covering a pond t weeks after beginning treatment to control the algae bloom. So apparently we've got this pond and there's algae covering it and we're treating it. And so because we're treating it, we're going to keep cutting down on the amount of algae there, right? We're trying to make it go away. Below is a table showing about how many square yards of algae remain during the first 5 weeks of treatment. So here it says we start out at time 0, we have 240 square yards, and then at time 1, now we're down to 80. Time 2, I don't know if is it weeks? It's weeks. So after 2 weeks, we're down to 27 square yards. After 3 weeks, we're down to 9 square yards. After 4 weeks, we're already down to just 3 square yards. So you can see that we have some kind of decay thing going on, and it's not by the same amount each time. I'm not just going from 240 to 280 and like subtracting 10 and then subtracting 10 again. So we want to, though, we're going to try and talk about average rate of change. So average rate of change is going to give us a sense of like when it's changing the most quickly. So I know that you and I can look at this and we can say like, wow, right away it's dropping from 240 to 80. That's really a big drop. And then later on from week 3 to week 4, it's only dropping by like 6 square yards. That's not as much. But our rate of change, finding our average rate of change, is going to give us a better, more mathy way to kind of talk about that. So when we did rate of change, we said, well, you're evaluating your function at 2 minus your function at 0 all over 2 minus 0. That's the way we did it in the last chapter. But if you recall, we really talked about how, hey, this is just a slope formula. So we could just use our slope formula that we're already really good at. And so I'm trying to find the slope between the 2 points. The point where I have week 0, well, week 0 is 0, 240, and week 2. And at week 2, I have 2, 27. So if we think about our ordered pairs, this is my x1, y1. This is my x2, y2. And my slope formula was just y2 minus y1 over x2 minus x1. I am still just doing a slope formula. And I can even just call it m. So m is going to be 27 minus 240 over 2 minus 1. So 27 minus 240, it works out that that is a negative 213. You know what? I wrote 1, but this is a 0, isn't it? It's 2 minus 0. 2 minus 0 is just 2. And then when we divide that out, let's see, 213 divided by 2, let's see, as a decimal, that's a negative 106.5. And let's remember, my top is my square yards. I totally spelled square wrong, sorry about that. And my denominator is those weeks, right? So like I'm just looking at how like A of t, these are yards and these are weeks, square yards and weeks. So I'm going to say this is negative 106.5 square yards per week. So on average for the first 2 weeks, we are losing 106.5 square yards of algae per week. So we didn't really lose 106 per week, did we? The first week we lost, it looks like 160. The second week we only lost, I don't know, 50 something. But on average, we lost 106.5 square yards per week. So that's why it's called average rate of change. We're kind of like averaging it together. So the second one we want to look at is from week 2 to week 4. So I'm going to do my slope formula again. Week 2 is 2, 27. And week 4 is 4, 3. So when I'm finding my slope, I'm going to take my y's and subtract. So 3 minus 27 divided by 4 minus 2. So that is negative 24 divided by 2, which is a negative 12. So this is much smaller. And again, these are square yards per week. So I am losing about 12 square yards per week. So now we're going to go ahead and compare our rates of change. So our rate of change from part A is much larger. Our rate of change is, I don't know, would you say it's larger or not? Because really it's a negative, so it's smaller, but there's a much bigger change in what's happening. Our rate of change, maybe we could say happens more quickly, or our graph changes more quickly. Let's figure out how to word this here. So like here it's 106, it's almost 10 times the amount. So maybe we could write it that way. Is almost 10 times bigger or more drastic, right? Lots bigger change happening. It's negative, but it's like shrinking really fast at first and then not so fast. From week 0 to 2 than from week 2 to 4. Right away, lots of algae dies off, and then the amount decreases less rapidly. So we're trying to get by this idea that this average rate of change shows us that right away there's huge drops in the amount of algae, and then later on not so much, right? Later on we're only losing about 12 square yards per week. So the difference, it should be difference, not difference. The difference in rate of change is due to so it's decaying a lot at first and not so much later on. It's really because we have a decay factor, growth or decay factor. I don't care which one you use. We have not talked about that a lot. Your book kind of uses the word growth all the time, but really if it's getting smaller, it's a decay. So if you're growing by, say, a third each time, right? You're not really actually growing. You're really getting smaller. But our multiplier is 1/3. So I'm going to write decay here and also growth. So I would expect either of those answers. If it's too difficult for you to figure out when it's growing, when it's decaying, if you're just really confused, we can always kind of refer to it as a growth factor because it is what we're multiplying by each time. But in this case, because we're multiplying by something less than 1, it looks like to get from 240 to 80, we really have a third left each time. So because we only have a third left each time and we're losing 2/3 each time, it's actually going to be decaying. So the difference in rate of change, so really fast at first, it's changing, and then not so fast later on, is because we have a decay factor here. All right, so this is just some more things to think about. It probably doesn't feel like we're doing a lot different. Doing the slope formula maybe is a little bit different this week, but we're still talking about how our graphs are changing. We're still coming up with equations for them. We're still looking at exponential functions. So as always, class, if you need help, please make sure you ask.